Okay. All right. Well, here we go. Let's talk about thin beams in shear again. Now, we actually had started this lecture earlier in the semester, and then I recognized, we only had a few minutes left at the end of a lecture, and we went into the first few slides of this. And then I realized that given the lack of being physically present, it was actually better to sort of reorder my lectures and give you one ahead of this one. I think it is now going to be helpful for our understanding of this material. So if these first few slides look familiar, it's because they are. Here we're going to address the issue of having thin beams in a shear carrying scenario, shear load carrying scenario. So these are beams who are in bending because, of course, shear leads to bending moments, and bending moments leads to bending. But we also recognize that this is a little bit more general than that as well. So as I had mentioned in our prior intro to this lecture a couple of lectures ago, we're going to redefine our coordinate system rather than starting at the centroid, although the centroidal coordinate system is still quite critical to us and very important for our understanding of the mechanics of the beam. It's not the most convenient coordinate system for doing things like integrating our stress, and you'll see that as we go forward why I say that's true. And so what we're going to do in this circumstance is we're going to define a new coordinate system. That coordinate system will be a tangent normal system, SN, where the normal is now defined in reference to the beam surface direction. So as we just even say those words, we of course recognize this thing that I alluded to a couple of lectures ago when we started this, is that we're going to make the assumption that this beam is now relatively thin. So I have my prop with me. This is that same foam pipe that I took off of my water pipes in my basement. And you can see now this, even though it's not terribly thin, thin in this context is really talking about the thickness of the wall relative to the total arc length of the beam itself. So this is a fairly thick walled beam in that sense, but it actually probably could be used for this thin wall theory reasonably well. And so what we're doing is we're defining a coordinate system at one edge of this, and then the coordinate system is tangent to the wall and has also a normal unit vector as well. So the normal reorients itself at every S location. And as we had talked about last time, we recognize that because of the governing differential equations of stress, if we have a traction-free surface, as I unroll this thing, if we've got a traction-free surface on the inside and we've got a traction-free surface on the outside, we can't have much of a stress, normal stress in this direction. Therefore, we can't have much of a stress gradient in that direction. And consequently, we're going to find that the shear stress is going to be relatively constant through the thickness, and we will in fact assume that to be the case. So we're going to have a constant shear stress through the thickness from the inside surface to the outside surface. We're going to call it tau ZS. It's on a Z face, so as I'm holding this, it's facing you. The Z direction is down the long axis of this beam. So Z face, S direction, so the stress associated with this resolves to a force that is tangential to the surface of the exterior surface of the beam. And now we're going to say that this is a function of two things. One is the Z location. That's the distance down the beam. And then number two is it's a function of the position S, so how far away from our coordinate system origin we are. Okay, just briefly highlighting this image. So we have shear resultants Sx and Sy on the thin-walled cross-section. And of course, because these ultimately lead to bending scenarios, we also have moments Mx and My on this cross-section. Now, you probably remember the bending lectures a couple of lectures ago, that there's a direct relationship between the resultant shear force on the face, Sx, and the resultant moment on that face, or in practice, it's actually the derivative of the resultant moment on that face with respect to the z-axis. So it's the total resultant on one face determines how the moment changes as a function down the length of the beam. So dmy, the moments about y, with respect to z are equal to minus sx. dmx with respect to z is equal to plus sy. We said that this was the plus minus differentiation there was based on the right-hand rule, and there's a shear to moment relationship. Now, one of the things that we've talked a little bit more about now is this idea of warping. Okay, again, warping is the in the z direction type of displacement relative to the other portions of the cross section. So whereas we previously had said plane sections remain plane, we can no longer say plane sections remain plane, and that's because this thing is thin and we get ultimately too much warping. And you could probably even see that if you happen to go to Home Depot and buy one of these and you tried to bend it, you can physically see a little warping going on. And so that's something that we need to be attentive to. Because of that, we need to develop a new formulation. You know, it's not as easy as describing the displacement as being linearly related to the position in the beam. Not quite that simple. So here's what we're going to do. We're going to define a new quantity. We're going to call that quantity the shear flow. Now, what does shear flow mean? Okay, really all what we're doing here is we're defining a term, we're calling it a flow, and now it becomes in some ways analogous to a fluid flow. Okay, and I'll get back to that a little bit more in a few minutes, but we're going to call it a flow. Now, when I say that, I'm saying that there's going to be some continuity requirements that we will eventually get to. We're not quite there yet because we haven't really defined the term yet, but I want you to recognize the word flow was carefully chosen in this definition. Okay, the other thing that we're going to do is we're going to define the variable we will use is just called Q. So the shear flow is Q, and it is equal to the shear stress at a point times the thickness at that point in the cross section. So if I hold up my small section, whatever the shear stress is, again, constant through the thickness, times that thickness, now gives us the shear flow. Now, I want you to pay attention to something as we've done that. The shear stress is constant through the thickness. We multiply it by the thickness. What's the unit on stress? Okay, shear stress is going to be, this is now unit terms, newtons per meter squared. Okay, if we're using SI units, or more generally, force per length squared. Now we're multiplying it by a length, and so we can cancel one of those, and now what we get is a force per unit length unit. So part of the reason why this definition is useful is because now we can define a force per unit length along the length of our section within the cross section. And it will make for a more convenient integration later, and we can get away with this because we're making the assumption that this stress is constant over the thickness. Okay, we'll get back to this idea of it being a flow in later slides. So keep that in the back of your mind as we can continue to talk about this. Now, the next thing that we're going to do is we're going to take our this, keep in mind, this is a beam. It's just a thin-walled beam now. A thin-walled beam. It's still a bending scenario. Okay, and when we look at that beam here, I'm looking at the left-hand side, this over here. As we are bending this thing, equilibrium still has to hold. Now, our equilibrium element in this context, rather than being a parallelepiped, we're actually going to take a little cut somewhere in our beam wall, such that we're getting a differential element that is of width ds, or delta s here as I've represented it. So it's a distance along this s direction, a differential length delta s, and similarly a differential length along the length of the beam delta z. So here we're going two directions. The total element is now the thickness times ds dz. That's the total volume of structure that we've made our equilibrium cut. And of course, all the same arguments about equilibrium still apply. That is, the sum of the forces have to be equal to 0. The sum of the moments have to be equal to 0. Of course, we could track acceleration terms. We're treating it as a static problem for now. So here now on the right-hand side is this element that we've defined. Okay, again, you can see ds, dz, the thickness in completeness, and then what is present here on this element as we've made cuts is the bending stress, sigma zz. Okay, again, that's pointing in this direction, stresses in this direction. So sigma zz positive on one side, sigma zz in the negative direction on the other side. That's obviously going to contribute to the forces. And then we have these shear flows, which I'm, again, much like we did previously, I said, shears, anywhere where we have corner adjacency, we need to have the shears defined in the same direction, either all in or all away from the corner. So that's what I've done here is I've drawn a shear flow, and you think of it as a shear stress times thickness. Here in this corner off to the right and to the left, so it is opposing there. Here in this corner, it's all converging in so that our signs are correct. And so what we have is shear flows on four surfaces, as well as normal stresses, sigma zz, ultimately on two surfaces. Why do I say only two surfaces? Because we're really, in this case, only paying attention to the things that contribute forces in the z direction. We're going to first take our equilibrium requirement, that is the sum of the forces in the z direction, have to be equal to 0. All right, now, so applying this formula, I'm going to say on the one side, much like we did with our prior calculations, we're going to say sigma zz on one side. We could say sigma zz at z plus dz. The way I'm actually writing this time is just going to be a change in differential, or I should say a differential change in the zz component. So on the positive side, we have sigma zz. On the negative side, we have sigma zz minus a small change. It's just a slightly different way of writing that same argument that we did previously. Similarly, we have on one side a shear flow Q, on the other side a shear flow Q minus a small change in Q. Now, if you pay attention to the arrows, the positive direction Z, so sigma ZZ minus sigma ZZ minus, and this of course would be in parentheses. So from that, we get sigma ZZ minus sigma ZZ plus delta sigma ZZ. So we have plus delta sigma ZZ times its area, because we need forces. So what is its area? Well, there's a differential length delta S in that direction, and there's a thickness in this direction. So that is now an area term. So delta sigma ZZ, delta S times T. This now becomes a differential force, a positive in the Z direction. That takes care of the normal forces. Now the shear forces on this front and back face don't contribute to the sum of the forces in the z direction because those components are in the s direction, and that's perpendicular to the z direction. So we don't get any contribution from this face here, nor from this face here to the sum of the forces in the z direction. That is, at least with respect to shear flows. So the shear flows contribute forces here, Q, and here, Q minus delta Q. We see the one on the right-hand side is positive. The one on the left-hand side is negative. So if we, essentially we're doing Q times Q minus delta Q. Okay, so the Q's cancel. The minuses become plus delta Q. Okay, so we get a plus delta Q. And now what we need, keeping in mind the unit on shear flow as we defined it was force per unit length. And so we multiply that by the unit length, delta Z, and that is the force contribution from the shears on these two sides of our differential element. So the total forces here are this equation. It's the change in the axial load over this differential element plus the change in the shear load. Each of those times their respective areas is equal to 0. And then we can obviously manipulate that a little bit. It's a good idea to divide by the differential lengths to put this now in the form of derivatives. And you can see what we have is going to be d sigma zz dz times t plus dq ds is equal to 0. Okay, any questions on that? Okay, so that was the z direction stresses, or z direction forces really on the differential element. The s direction equilibrium also needs to be applied. So we're going to now sum the forces in the s direction. And if we were to look at those, I haven't drawn the, in fact, I probably should. Let me go ahead and do that on the side over here. So here's my differential element. Now we have the normal stresses sigma zz, sigma ss, and we have the corresponding on this side over here, sigma ss. Okay, we have a differential from one side to the other, so we can do plus delta sigma ss over this length delta s. So those are going to contribute to the s direction forces. So that times its area, which is delta z times t. So it's this length times the thickness. So that's where we're getting this differential force from. And then the other argument, of course, is similar to what we had on the last slide. That is this one up here, that now we have terms that contribute on these faces to the s direction stresses, and that ultimately manifests itself as delta q times delta s, and all in what we get is this equation. So these are two equations now that we've written for a differential element, a small little cut of the thin-walled beam section. And what it does is it relates the shear stresses in the form of the shear flows to the normal stresses, and they manifest themselves as differential equations. Okay, in the limit as delta s goes to 0, we get by definition here a derivative, partial q partial s is going to be equal to minus t d sigma zz dz. Okay, another interesting thing that can occur here is that if we're applying the shear forces such that no twisting occurs, then sigma SS is going to be equal to 0. Now, what do I mean by that? If I'm applying this in a way that doesn't generate twisting, then sigma SS is 0. So when sigma SS is 0, the sigma SS ds also goes to 0. That goes away. dq dz is equal to 0. So now q is going to be a constant with respect to z, and that leaves us this equation as the governing equation. dq ds is equal to minus t d sigma zz dz. Okay, it's worth noting a couple of things with this equation. First of all, one might say, well, you're going to have twisting sometimes. Okay, and I agree with that. So when that's true, then this is problematic. However, and we've made this argument now a couple of times, we actually proved why we could do it earlier. Remember how we said we can decouple axial load from bending, and we can decouple twisting from bending and twisting from axial load? So if we treat this problem with a superposition thought process, that means that we can compute the twisting separately and ultimately add it back to whatever solution we have now. So that means for all of our bending of thin-walled structures calculations, we can assume that there is no twisting as we formulate our approach, and then we add the twisting in later. So this equation deals with the bending aspects of thin-walled structures, and we don't need to worry about twisting for the time being. All right, I know I'm going fairly quickly through this. I hope not uncomfortably slow, or uncomfortably so. So if you're falling behind, ask me a question in the chat window, or pop in on the mic and ask those questions, please. Tough for me to discern if you guys are following along or not, seeing very small pictures on the screen, but I don't want to leave you behind. Okay, now, so as we look at this equation, what did we see? This is from the last slide, dq ds. This equation on the left-hand side, what does this mean? We need to interpret it. It's not just some variables. They actually have meaning. Q is the shear flow. Q is the shear flow. Now, what we're saying here is the shear flow doesn't change with respect, it does change. It changes with respect to the S direction. So the shear flow changes as we go around this section. How does it change? It relates to the bending stress sigma zz. So the shear flow is governed by the bending stress. The shear flow is governed by the bending stress, and it's done so with this equation. I see Nicole asked a question, how do you go from delta Q, delta Z equals 0 to the differential equation? To which differential equation? Nicole, I'm going to give you some time to pop that into the chat window here in a minute. Yeah, go ahead.
I was kind of confused about how you went to the on the next slide. That one. How you get the equation in the box there. I think you said something about taking the limit of equation 8, but then you also said something about crossing out the sigma SS. So I'm not really sure.
Yeah, so these are two different equations are driving our scenario here. So one of them is the sum of the forces in the Z direction. The other is the sum of the forces in the S direction. Okay, now let me jump back to this slide here for a minute. So this slide has the sum of the forces in the z direction. And ultimately what we do here is we're going to move this to the other side and then take the limit as delta goes to 0. And then this leads to this equation.
So it came from the other equation on the other side then?
Yes, and I see, you know, this is, honestly, this is the first time I've taught this class where I've had to do it on slides, and I can see how this could be confusing because I should have probably highlighted this equation on the prior slide. So I'll do that, I'll make that change and update it later. But so this equation that I've now circled ultimately comes from this equation, taking the limit as delta goes to 0. And then this other set of equations is actually, you know, again, this equation comes from the sum of the forces in the x direction. We can again take the limit as delta goes to 0, and that drives this to be a derivative. Okay, and when sigma SS is 0, which we can do if we isolate bending from twisting by decoupling them, which we've already proven we can do. So we're going to assume we're going to do that, and so therefore sigma SS would be equal to 0. If sigma SS is 0, then its derivative is also 0, and then this is what's remaining, and this is just dq dz is equal to 0. So that is something that we will come back to later, but is perhaps less relevant than this equation right now. And thank you for asking this question, because this is clearly highlighted that really this should be on the prior slide, and I'll make that change and upload it to the future you know, versions of this presentation.
I also had a question. This is Garrett.
Yeah, hi Garrett.
Is the S direction basically the X or Y direction?
No, great question. So if I wasn't clear about that, in fact, I admit that I didn't clearly describe that. Let me touch on that a little bit more.
Yeah,
okay, so
picture that you were holding up, or the foam thing.
So here's the cross section that I've drawn. Now, just keep in mind this is meant to represent a general thin-walled section. So I said in the image that I presented on the prior slide, I said we're going to say S starts here. And oh, by the way, it has a corresponding perpendicular N. Okay, so we've got a tangential direction and we've got a normal direction. Normal relative to the surface that this thin-walled beam sweeps out. So if we looked at a different location here, we've got a new N and a new S. Again, these are perpendicular here, but the S directions are not the same. The N directions are not the same. So what we're doing here is we're following the line, essentially following the midline of our thin wall as defining our coordinate system. So the S direction follows the midline and then has a, of course, perpendicular direction to it as well that we're going to call N. So there are going to be times where S corresponds with the X or Y directions, but as a general rule, it doesn't. So thanks for that question, Garrett. Anything else that I've kind of left in a confusing state here? I want to make sure I'm cleaning them up as there's anything left. Okay, now let me highlight this equation one more time. So what we have learned is the relationship between the change in Q with respect to the S direction and the bending stress. Now we know, because of the beam bending equations, we can write down directly what sigma ZZ is. So that's what's coming up on the next slide, sigma ZZ. And you remember from our beam discussions that the sigma ZZ, the bending stress along the axis, is equal to the modulus times the curvature times position. Right, so E minus U comma ZZ, so that's curvature, times X position, minus V comma ZZ, curvature in the other direction, times Y. Now, in the equation above, we saw that the change in S was related to the change with respect to Z, d sigma ZZ dZ. So we're going to immediately take the derivative of this equation, and in this case, I'll just call it sigma ZZ comma Z, is going to be equal to everything we had before, comma Z, which then the derivative propagates inwards to our equations. Okay, it will propagate in. I'm leaving it outside for the time being for clarity. Okay, but it will propagate in over time. Now, the other thing that we did in our beam bending discussion was we had put these equations in a matrix form. So we had M as a vector of length 2 on one side. We had the EI matrix, 2 by 2, times the curvature, curvature vector, 2 by 1. Okay, so this was mx and my is equal to a matrix of EI terms times the curvatures U comma ZZ and V comma ZZ. Then the next thing we said we could do is we can invert that, and we get this U comma ZZ is equal to the EI inverse times the moment equation. Okay, so this is the second derivative, curvatures here, times the, and this functionally ends up being the matrices that arise here end up giving this equation. So sigma ZZ was written as E over the determinant of EI, that came directly from the inversion, times now minus X EI XY MX, that's this term here, plus EI XX MY, that's also this term. It's just a different row times a different, it's this row times this column brings out these terms here. Okay, plus Y, notice here the position is still present, and then we have Y times EI YY MX plus EI XY MY. Now I've still kept the derivative outside to make the moments clear in this equation. And then last but not least, we propagate the derivatives in, and you remember, I hope, the relationship between moment and shear force. That's one that we've actually used just today, and forgive me from bouncing around a little bit. That is this equation. dmy dz is equal to the shear resultance with appropriate signs. And so this term here, when we had moments in it, and then we take the derivatives, becomes shear resultance. So sigma ZZ comma Z, the derivative of ZZ with respect to Z is now E over the determinant of the EI matrix times these quantities, X EI XX SX minus EI XY SY plus Y EI YY SY minus EI XY SX. All right, I did see a question coming through. I'll address that in just a moment. So let's see here. So David asks, is that U on the left-hand side of the orange equation? This here is going to be U comma ZZ V comma ZZ. So this is the curvatures written as a 2 by 1 vector.
So is the left one V and then you wrote U?
The left one V.
upper hand left corner.
Upper left-hand corner. This one up here? Oh, this was an M here.
Thank you.
So these should have been the U comma ZZs here. It's really surprisingly hard to write with my mouse, and I'm terribly disappointed in the tablet's lack of precision when we were trying that earlier in the semester. Okay, so those equations both were derived in the beam bending talk. Again, I should make some notes to myself about how to make this more clear coming forward. I should just copy those equations and paste them here so that I don't have to write them down. Anyway, improvements still to be made, obviously. So what do we conclude? Well, we can conclude what the relationship between the bending stress is. Its derivative with respect to the z direction is now related to the S values, the shear resultants. Ethan asks, I presume we're using this form of sigma zz because W0 comma z is equal to 0, since we assumed there was no warping. This actually goes back, Ethan, to the bending lecture, where we said that the axial stress due to axial deformation can be treated separately and then summed at the end. Okay, so we're saying the twisting and the axial loads are not a part of this calculation. They are treated entirely independently and then use linear superposition to bring them together at the end of the day. And that's where that W0 comma Z would reside. It's in the axial resultant force equation. Okay, now let me go back to this just a little bit here. There's some things to note. So the determinant of the EI matrix is actually going to have some EIs in it. In fact, the E values will end up canceling. Okay, if you go back to that lecture and see precisely how EI was placed, there were a couple of EIs in there. In fact, you got E squared in that determinant. And then here we have an E times an E. Okay, so we have E squared in the numerator, E squared in the denominator. Those things ultimately cancel. What then remains is just the I values and the S values and the positions X and Y. And so when we do that, we can write this equation, the derivative, and it's going to be written ultimately just in terms of the I values and the S's. Now, before we totally get to that level, we also have to recognize that this is a derivative equation. The derivative with respect to S can now be written where we know what sigma zz is, and importantly, we know what its whole derivative is. And so the next step will be to integrate this equation. So if we integrate this on the left-hand side, and we integrate this on the right-hand side, what we get, the left-hand side becomes Q of S. So the integral of dq ds is Q of S plus a constant. Okay, we can, and on the right-hand side, we would also get a constant, and so we're only going to keep one of those two constants because you could just add those constants together. I'm going to treat the whole thing as being on the left-hand side, and I'm going to give it a negative sign. Okay, that's just a convenient way to treat the constant. And on the right-hand side, we're integrating all these terms that were present in this equation. And after the e's cancel, we're integrating X, I, and S. But keep in mind that I and S are resultants over the entire area of the cross-section. The area moment of inertia and the resultant load over the entire cross-section are both independent of where you are in the cross-section. So they can come outside the integral. So all of these terms here both in this top level and the bottom level, are constant with respect to the integral, and what remains inside the integral are only the things that are now functions of S. This integral proceeded, we were integrating with respect to the S variable. So now we're going to say that what is unknown, or what is not constant, is the X position times the thickness. And we're integrating from an initial S set at S equals to 0 to some final S. So the constant we defined as Q at S equals 0, and then the equation, the integral begins at 0 and goes to S. Okay, I recognize this is a little bit difficult to swallow conceptually. It's harder to do this with slides than it has been traditionally to do this on the chalkboard. So if anybody's confused, let's try and clean up that confusion now. I'm going to pause for just a second while you guys wrestle with it. Are you guys comfortable? Give me thumbs up if you understand what's going on. I'm seeing a lot of this and not a lot of this. Okay, so Ethan, I saw, Ethan, you're one of only 5 people on my screen right now. Can you tell me what you're not certain of? You were demonstrating that you weren't certain, but you sort of followed. What's uncertain?
I'm trying to formulate what to ask right now. I'll get back to you in a second.
Okay, that's fair. Hannah, you're one of the other few people on my screen right now. Can you formulate a question to help clarify what's confusing?
I'm not sure it's really a question. It's more of just like trying to visualize slash conceptualize it kind of thing. Like I just need to like look at it for a bit, and then maybe in practice it'll be more clear, like using the equation.
Yeah, okay. Let me see here. I might be able to. I think maybe what's confusing is, no, it's not that. Okay, ladies and gentlemen, on my main computer, I disconnected myself. It's going to take me just a second to get back in on that main computer, so sorry about that. I'm almost there. Okay, I think I'm back set up now. I just need to go ahead and present one more time. So I accidentally blew it away when I loaded up the wrong presentation and then tried to close it. It ended up closing all my Firefox windows. That one was connected to the meeting here. So just so you remember exactly where we were, this is that set of matrices that I had referred to earlier. So on the left-hand side is the curvature and the right-hand side is the inverse of the EI matrix and the moments. Okay, the other version of that was this. Okay, so the moments on the left-hand side are equal to the EI matrix times the curvatures. We needed the curvatures to be free on the left-hand side, so we just did this matrix inversion. By doing the matrix inversion, we end up with this determinant of EI statement. It's in the denominator. You can see that in this, we have E times E minus E squared. So this ends up being E squared times EIXX IYY and minus IXY. Okay, now this we have to plug into the this equation now, and now I got to find my page again because I fell behind a little bit. So if we plug that into this equation here, where we have the EI's in the numerator, so we're going to cancel the EI squared and then bring this down to this relationship. Okay, Ethan says that he's a little bit more confident now. He found an error in his minus signs. I'm not sure, Hannah, if I've totally cleared it up for you. We'll continue forward here unless anybody objects. Certainly, of course, come back in with questions if you're still confused. I think maybe it's a little better now. Okay, so notable in this, of course, is that if we have, this is for any cross section really, if we have symmetry in the cross section, of course, we recognize that the XY terms go away. And then that simplifies this to be a much cleaner set of equations. And in fact, a lot simpler because we lose the denominator term, a big chunk of the denominator term, and we ultimately separate Sx from Sy. But still what's present here as it was in the prior equations is this integral. The integral of xt of s ds and yt of s ds. Okay, so in summary, what have we done? Okay, over the last 25 minutes or so, we said, okay, if we observe the geometric thin-walled section, in addition to all the beam bending assumptions that we've made previously, we can make one more assumption. And that assumption is that there's no variation through the wall thickness because the through the wall thickness stress, sigma nn, normal to that wall, that's going to be 0 because it's traction free on the outside, it's traction free on the inside. Consequently, we're going to have constant shear stress across the thickness. Thus, we can define this convenience term called the shear flow. We can relate that shear flow to bending, ultimately after a little manipulation through this equation here. I know that's clear as mud. Let's do an example. I think it's going to be more clear after we do the example. So the example I'm now presenting actually used to be a homework problem I've assigned in the past. I decided to make it a lecture example because I think it's a nice demonstration. Here is the cross section that we're looking at. We're going to call it a hat section because it, roughly looks like a fedora or something. We're going to have 3 equal length sections, actually 5 total sections. The total width of this is 3L, so something that is of width, thickness TA for length L on the left-hand side, thickness TA over a subsection L on the right-hand side. It is going to be symmetric about the y-axis. We've got vertical shear webs here that are going to be thicker than the flanges at the top and the bottom. So TB is going to be thicker than TA. We'll just track them separately with 2 different variables. And what we're going to do is we're going to apply a shear resultant, SY, on this cross section. Okay, now when I say we're applying a shear resultant, imagine I'm deforming this thing, I'm bending it. Okay, the total force over the entire cross section is going to be a shear force of magnitude SY in the Y direction. Now I happen to have drawn it such that the resultant happens to be on the line of symmetry. That makes this calculation easier for us today. So that's the way we're going to demonstrate it this time. So the shear resultant goes through the line of symmetry. What else do we know? We actually know it goes through the centroid, because the centroid will lie on the line of symmetry for a problem like this. And so that is another convenience for doing the problem. In general, we couldn't always say that was true. It would be perfectly legitimate for me to give you a problem where that were not true. But in this case, that's what I've done. So this is the setup, and the question then becomes, plot the shear flow and shear stress in the section. And it's most conveniently plotted actually as a function of S rather than X and Y positions. And you'll see why in a few minutes when we get to the end. I see a question from Nicole has come in. So when you take the integral of both sides of equation 15, I'm guessing you multiplied the ds over to the right-hand side, but what happened to the dz? Okay, so the dz, so this a great question, Nicole. So first of all, to integrate with respect to s, so on the left-hand side, this becomes dq ds integral ds. So I multiply by ds. Boy, that's terrible handwriting. Partial q, partial s. So the integral of the left-hand side with respect to ds, so I multiply by ds, you're correct in stating that. That's how I end up with q being the thing that is recovered. When we cancel the ds's, we're then integrating dq and we get dq. So great observation there. On the right-hand side, you asked, well, what happened to dz? So dz was taken care of in this prior equation where I had calculated the stress, and then I calculated its derivative with respect to z, which gave us this set of values, which no longer have the dz in them in that sense, right? We took the derivatives, and this is the result. And then ultimately, once that gets plugged into the right hand of the equation, we integrated, like we did with the left-hand side, we multiplied by ds. So we took everything over here, multiplied by ds, and took the integral, and that's where the ds lives here. Okay, so I hope that's clear. That was a great question that maybe, again, lacked some clarity on my description. So wonderful, thank you. Anyway, so let's get into this. What's the shear flow? That's the answer. What's the shear flow? I've got a thin-walled bending section. What's the shear flow for this shear stress resultant? For the sake of argument, we will eventually assume some values on these variables, although we don't need to for the time being. We will find that this is a 300 millimeter by 20 millimeter thick. So the two thicknesses are 20 millimeters and 30 millimeters. The overall length L is 300. Of course, there's 3 times that, so 30 centimeters. This is going to be a big section, okay, big section with a relatively low load 200 newtons, but that's not really critical. We're going to do this predominantly with the variables so you can see it without losing its physical interpretation. Hint here, when you do the plot, you should plot S on the abscissa and the shear stress and shear flow on the ordinate. So, and I'll show you that later. Okay, so, well, the solution is what I gave you here is Q. We can calculate the shear flow. Okay, the right-hand side is the integral, the left-hand side is Q. I've moved just for the sake of compactness on the integral, the Q0 to the right-hand side. It was more compact on the left-hand side previously. Now I've moved it back to the right-hand side, so I added that plus. This was the complete equation for an asymmetric cross-section. However, for a symmetric cross-section, of course, we're going to go, which this is, by the way, so this is symmetric about the y-axis. So we're going to go through and we're going to cross out the xy components everywhere where they exist. And lo and behold, we get this equation. The last thing I'll say is, going back one more, we also, per the definition of the problem, I had no SX resultant. So there was no SX present. SX is equal to 0. When that goes away, then this goes away, which actually wipes out everything here. Boom, that whole thing goes away. The Q has not gone away, it's still there. So when we get rid of the SX and we get rid of the IXY, there's a lot of stuff that goes away, and we end up with this relatively simple equation by comparison. QS is equal to the initial stress, so that's the integration constant, minus the integral from the starting point to the ending point of T of S, Y of S, ds. Now times the shear resultant Y over IXX, the area property of the cross section. Okay, now can we compute this integral? Well, yeah, of course we can. This is actually going to be trivially easy, and I'll take you through it so that everybody's confident that they can do it on their own. In this problem, it will be trivially easy. In some problems, it gets a little harder, but that'll be what the homework is for, to practice that issue. Okay, now, I'm going to make the argument. Now, just so you're aware, I kept this image on the screen so we can zoom in constantly, but we're going to have enough stuff on the screen that I kept it relatively small. I want to pause for a second and remind you guys what an integral is. In fact, let me ask you what an integral is. What is an integral? Now, it's the same 5 people I see on the screen. I'm going to change my screen so I see a few more, hopefully. I'm going to pick on somebody here. Shoot. How about Tyler? Tyler, you're the number 6 person on the screen. I've called on the people above. What's an integral? So Tyler's remaining relatively silent. Amir, you're next. What's an integral?
I would say a sum.
It's a sum. That's the great answer I was looking for, precisely. Okay, thank you. So an integral is a sum. Okay, now we can do that whole integral in one shot. That is this integral. Or we can break that integral up into smaller sums and do it a little bit at a time. Okay, I think you guys would all be comfortable with that, recognizing that an integral is nothing more than a sum. So what I'm going to do is I'm going to break the integration up into 5 different integrals, one for each section, one for here, one for here, one for here, one for here, and one for here. Violating no rules, an integral is a sum. We're going to do it in 5 parts. And the next thing I'm going to recognize is within this integral, again, this is this integral here, we know for the cross section certain properties that exist in this integral. So for example, we know in section 1, we're going to call this from here to here section 1. We're going to call this from here to here section 2, and likewise section 3 and section 4 and section 5. So as we stare at this screen, we see that the items in the integral can be expressed quite simply within just one segment. Okay, so from here to here, we can say that the thickness is a constant. Oh, by the way, we can say the value of y from here to here is also a constant within the sub-integral that goes from here to here. Hence, what I'm doing on this slide is writing the values of the things that are present inside the integral. So we know the integral is, what is it? It's ty ds. Ty ds. And then, of course, we also had the integration constant, which we need to track separately for each subsection. So for that section, from the left edge to the first vertical component, the thickness as a function of S was a constant value TA. The Y value for that segment is a constant value. Now, the only caveat here is that the constancy, the value of Y is relative to the centroid. So if I were to go back and draw the centroid on here, we haven't computed where it is yet, but I bet you your instincts tell you it's somewhere in here. Okay, if we know it's somewhere in here, then the distance from here to here, we're going to say is equal to minus y of the centroid. Okay, and last but not least is this shear flow integration constant Q0. So we need to have some idea of what that one has in its magnitude. It is an integration constant. So as I stare at the left-hand edge, we start, this is Q at S equals 0, so S equals 0 here at the left edge. What do we know at that point? Keep in mind, what is Q? Q is the shear flow, which is also the shear stress times the thickness. So that's a very strong hint. What do we know is occurring? Let's see here. At this edge, I got to try and make this more visible to you. What do we know to be true over here for shear stress? This edge is traction free, right? It's hanging out at the edge. There's no stresses applied to that edge, traction free. So the shear stress is equal to 0. So 0 times the thickness, the shear flow, is also equal to 0 at that location. Okay, so we're just doing bookkeeping really now. These are really easy things to identify. So at this location for the subsection 1, the left edge, we know that T is constant TA, Y is constant YC minus, and Q0 is 0. Okay, we can then look at the next segment. And what do we see there? Again, going back to this image, when we're now looking at the integral from this location up to this location. For this segment of the integral, the thickness is constant TB. Okay, we are going to need to track the integration constant at the edge, and we're going to have to track the Y location. Okay, in this case, Y is not a constant as it's regarding to S. Okay, as S changes in this segment, so does the Y position. So we have to write a function for Y in here, and that's really the only challenge to this portion. But as we look at what these are, we can see that the thickness for this second S segment is constant TB. We can write the Y position as starting at a value which we had previously established, And then for every increment in the S direction, we increment in the Y direction. So it ends up being minus YC plus S2. And then last but not least, the integration constant as we start at this location where S2 is equal to 0. Well, we don't know much about it yet, but we do know that it is equal to the value of Q as we have moved from, let's see here, go back to this. So we said Q was 0 at the left edge, and as we were integrating across this area, we get to a value of Q here. And so the value, the initial Q at this location for the second segment is equal to the value of Q as we integrated from the left edge to that location. So this is a continuity argument in shear flow. The shear flow has to be the same at this location at the right side of segment 1 as it is at the bottom side of segment 2. So going back to the table that we've created, for subsection 1, we know all the values inside the integral. For subsection 2, we now know the values for the integral. We can go back to section 3, and it starts to look easy again. What do we know? We know the thickness is constant. We know that the value of y is constant as s changes. And we know that the value of q at the beginning of this segment is simply the value of q integrated. You know, it's the continuity argument. So as we go from S2 equals 0 to S2 equals L, we know the value of S2 equals L is the starting value for the next segment. And that argument is going to apply for each of these segments in turn. Okay, so for segment 2, y is constant, t is constant. For segment 3, t is constant, the thickness is constant, but y is changing as a function of s, and we'll write an equation for that. And for the last segment, both y is constant and t is constant. So in the 2 vertical segments, y is a function of s. In the 3 horizontal segments, it's a constant. They're all constant thicknesses, although they change as we go from segment to segment. And in total, we can write down now all of these values. For subsegment 2, the thickness is b, and the y is a function of s. For subsegment 3, the thickness is constant TA, and the position, y position, is a constant. It's not a function of s. It's L minus YC, and the initial Q is the final Q from the prior segment. I'll just include all of these and stop talking for a minute while you guys jot them down. The 4th segment, y is a function of s. The 5th segment, y is a constant. In all cases, within the various integral portions, the t is constant. Okay, we're actually slightly over time already. Let me get you to the punchline, and we'll return to this next Tuesday. It's notable that in each of these above equations, we defined a local S value, and we set an appropriate boundary condition. I said there was S1, I said there was S2, I said there was S3, I said there was S4, and S5. Each had their own appropriate boundary condition for the value. The global and local S coordinates are shifted by the position along the beam according to the local coordinate system. All right, I think, you know, we are a few minutes over already. We're actually 4 minutes past. I think stopping there, it's a good place to pick up again next time rather than trying to rush through. So what I'll do is I'll leave these equations back on the screen. I know some of you were maybe trying to jot them down rapidly. So now you're going to have time to do that. I'll hang out for just a few minutes as I usually do after lecture, although I have to be in another meeting for a thesis defense in about 4 minutes, so I'm not going to be able to hang out for too long.